What if time did not move the same everywhere? What if one person could experience only a few minutes, while the rest of the universe moves forward by years? It sounds like science fiction, but near a black hole, this is real physics. Black holes do not just trap light. They do something even stranger. They change the flow of time. To understand why, we need to begin with one of the greatest discoveries in science. Time is not separate from space. In everyday life, we think of space and time as different things. Space is where objects exist. Time is what clocks measure. But according to Einstein's theory of relativity, space and time are connected. Together, they form something called spacetime. And spacetime can bend. A planet bends spacetime a little. A star bends it much more. But a black hole bends spacetime so extremely that once you get too close, not even light can escape. This is where time becomes strange. Gravity does not only pull objects, gravity also affects time. The stronger the gravity, the slower time passes compared to places with weaker gravity. This is called gravitational time dilation. And it is not just a theory. It happens around Earth too. A clock closer to Earth's surface ticks slightly slower than a clock far above Earth. The difference is tiny, but it is real. Even GPS satellites must correct for relativity, because time does not pass exactly the same in orbit as it does on the ground. If scientists ignored this, GPS would slowly become inaccurate. So time dilation is already part of our everyday technology. But near a black hole, the effect becomes extreme. Imagine a spaceship traveling toward a black hole. Far away, everything feels normal. The ship's clock ticks normally. The crew moves normally. Their hearts beat normally. But as the ship gets closer, the gravity becomes stronger. And as gravity becomes stronger, time on the ship begins to slow down compared to time far away. The strange thing is this. The astronauts would not feel their own time slowing down. To them, everything inside the ship would seem normal. Their voices, their thoughts, their movements, and their clocks would all feel ordinary. But to someone watching from far away, the ship would look very different. It would appear to slow down. The closer it gets to the black hole, the slower it seems to move. Its light would become stretched. Its image would become dimmer and redder. This effect is called gravitational redshift. Light loses energy as it climbs away from the intense gravity of the black hole. So from far away, the falling spaceship would slowly fade. It would appear to freeze near the edge. That edge is called the event horizon. The event horizon is the point of no return. Once anything crosses it, escape becomes impossible. Not because there is a solid wall. A black hole does not have a surface like a planet. The event horizon is a boundary in space-time. Outside it, escape is still possible. Inside it, every possible path leads deeper into the black hole. Even light cannot find a way back out. From the outside universe, something falling toward the event horizon never seems to fully cross it. It gets closer and closer and closer, but appears to slow down forever. To a distant observer, time near the event horizon looks almost frozen. But from the perspective of the person falling in, the story is different. They do not freeze. They do not see time stop. They keep falling. If the black hole is very large, they might even cross the event horizon without noticing anything special at that exact moment. There would be no wall, no surface, no warning sign, just a silent boundary where returning becomes impossible. That is one of the strangest things about black holes. Two people can disagree about what is happening, and both can be correct. From far away, the falling person appears frozen. From their own perspective, they continue moving normally. This is not an illusion, it is relativity. Time depends on where you are and how strong gravity is around you. Now imagine two astronauts. One stays far away from the black hole. The other travels close to it, spends some time near the edge, and somehow escapes. When they meet again, They may no longer be the same age. The astronaut who went near the black hole could have aged less. For them, maybe only hours passed. But for the astronaut far away, days, months, or even years could have gone by. This means a black hole could act like a natural time machine, not a machine that takes you into the past, but one that pushes you into the future. By spending time near extreme gravity, your time slows down compared to the rest of the universe. When you return, the universe has moved ahead faster than you have. But this kind of time travel comes with a terrifying risk. The closer you get to the black hole, the harder it is to escape. And once you cross the event horizon, there is no turning back. Inside, your future points toward the center, toward the singularity, a place where gravity becomes so extreme that our current laws of physics break down. For small black holes, you would be destroyed before reaching the event horizon. The gravity near your feet would be much stronger than the gravity near your head. This difference would stretch your body apart. Scientists call this spaghettification. But for a supermassive black hole, the event horizon can be much larger. The tidal forces at the edge may be weaker. In theory, you could cross the event horizon before being torn apart later. But either way, the result is the same. Once you go too far, the black hole owns your future. So why does time slow near a black hole? Because gravity bends space-time. And near a black hole, space-time is bent so strongly that time itself is stretched. To a distant observer, objects near the event horizon appear to slow down and fade away. But to the falling object, time continues normally, even as escape becomes impossible. That is the terrifying beauty of black holes. They are not just dark objects in space. They are places where time, light, gravity, and reality are pushed to their limits. They show us that time is not universal. A second near a black hole is not the same as a second far away. And somewhere beyond the event horizon, hidden from the rest of the universe, lies one of the greatest mysteries in science. A place where space and time may come to an end. This is why black holes are more than cosmic monsters. They are windows into the deepest rules of reality. They do not just swallow matter. They reveal that the universe is stranger than we ever imagined. This is Frontiers of Vision. Subscribe for more cinematic journeys into space, science, and the future.